This video is an example problem for related rates, specifically example 2, the high-speed chase. Take a moment to pause the video and read example 2. By this point, you should have paused the video and read example 2, which is about a police car approaching a right-angled intersection and seeing a speeding car leaving that intersection from the east. As you read the problem, it's a good idea to circle key information, which has been done on this problem here. In order to solve this problem, we are going to draw the right-angled intersection. It's always a good idea to start with a sketch when you're solving a related rates problem. I know that the police car is to the north of the intersection, so we're going to put a dot here for the police car, label it P. And I know that the speeding car is to the east, S for speeding. This distance is P, and this distance is S. I know we labeled the points, but we're going to consider those the side lengths of the triangle. Now, the distance between the two cars is this third leg of a right triangle, which I'm going to call L for the length between them. All of these lengths are changing, and they are related to each other. Hence, related rates. The police car is moving south, the speeding car is moving east, and the distance between them is getting bigger. You can see that it's increasing. So, the police car is moving south, meaning that this change, dp dt, is going to be a negative number. The speeding car is moving east, which means that this change, ds dt, is going to be a positive number. The length between these two cars is also changing. It is growing. So dl dt is the rate that is growing. At the moment, we've been given some information. P, the police car, is 0.6 miles. Oh, I'm sorry, 0.8. 0.8 mile, or 0.6. The police car is 0.6 miles to the north. The speeding car is 0.8 miles to the east. And at this point, I should notice that I have not been given L, but that is something I can solve for. Making a triangle, 0.6, 0.8. I can solve for this third side using the Pythagorean theorem. At this point, you should pause the video and compute that yourself. After you have paused the video, in order to solve for this third side of the triangle to find L, I notice that these sides are in proportion. So if I multiply them, I can get a triangle I know, which is the 3, 4, 5 triangle. If I double each of these sides, so times 2, times 2, times 2, I would get a 6, 8, 10 triangle. But this is 0.6, 0.8. So this is actually going to be 1.0. The third side is 1.0, which is L. At this point, we should notice that there is a right triangle involved in this problem and only side lengths. So in order to solve the related rates problem, I'm going to choose a formula, and the formula I'm going to use is the Pythagorean theorem. My sides are P, S, and L, so P squared plus S squared equals L squared. All of these quantities are changing, none of them are constant, and all of the variables matter. I cannot substitute anything out. I'm ready to differentiate. D dt. Of course, we're going to be using the chain rule 3 times here. There are no products or quotients. 2p dp dt is the derivative of p squared, plus 2s ds dt is the derivative of s squared, equals 2l dl dt, the derivative of L squared. Now I can plug in quantities that I know from my given information. So I'm going to have 2 times p is 0.6 miles, dp dt, which is this 60 miles per hour. So miles per hour tells me it is a rate. That's the rate the police car is moving. So dp dt is going to be the 60, but it is going to be negative because this distance is shrinking. mph. Similarly, dl dt is this 20. That's the distance between the car and the police car and the speeding car. That is a positive 20 miles per hour. So 2 times p, which is 0.6, times dp dt, which is negative 60 miles per hour, plus 2 times, I know s, that's 0.8 miles, ds dt, I'm solving for that, equals 2 times L, which we solved was 1 mile, times dL dt, which is the 20 miles per hour. Using some simple algebra here, 2 times 0.6 times negative 60, that is negative 72 miles squared per hour, plus 2 times 0.8, that's 1.6 miles, ds dt, equals 2 times 1 times 20, so that is going to be 40 miles squared per hour. Combining like terms, we will add 72 miles squared per hour to both sides. We will be left with 1.6 ds dt, which is again what we are solving for. We do not want to lose that ds dt, is 112 miles squared per hour. This is 1.6 miles. We're going to divide both sides by 1.6 miles. Canceling out, and we will have that ds dt is 70, and then these miles cancel, miles per hour. That is a positive rate. It is a reasonably fast rate for a car. That is a reasonable solution. At this point, I would like you to try related rates multiple choice practice number 4. Thank you for watching.